Atmospheric whispers of technology. Beyond energy harvesting methods that might reveal advanced aliens, their planets themselves tell stories through chemistry that no civilization can easily hide. The James Webb Space Telescope now provides humanity with unprecedented capabilities to read atmospheric pollution signatures across light years of space, and certain compounds would be impossible to explain through any natural process. This chemical evidence may prove more reliable than radio signals in our search for technological neighbors. Think about what happens when a civilization industrializes. As they build factories, generate power, and manufacture goods, they inevitably release chemicals into their atmosphere. These emissions function as persistent calling cards that linger for decades or even centuries. What makes these atmospheric markers so valuable in our search is that some industrial compounds simply cannot be created through any natural biological process. Nitrogen trifluoride exemplifies this perfectly. This industrial compound plays a crucial role in Earth's electronics manufacturing, specifically in creating semiconductors and LCD displays. The production process involves specialized plasma chambers, where nitrogen and fluorine atoms are forced to bond at high temperatures. NF3's strong nitrogen-fluorine bonds make it valuable for precision etching of silicon wafers, but these same bonds have never emerged in any known natural biological system. Similarly, sulfur hexafluoride, used in electrical insulation and medical imaging, contains sulfur-fluorine bonds entirely absent from natural biochemistry. These artificial compounds create distinctive fingerprints in a planet's spectrum. When starlight passes through an exoplanet's atmosphere during transit, each molecule absorbs light at specific wavelengths, creating a unique pattern in the resulting spectrum. Industrial chemicals stand out dramatically, equivalent to finding a plastic water bottle on a pristine beach. The power of this detection method lies in its unavoidable nature. While a civilization might choose to stop broadcasting radio signals, they cannot easily erase the atmospheric evidence of their industrial development. Even if an advanced society transitions to cleaner technologies, the chemical ghosts of their technological progress would continue to haunt their atmosphere for generations. Leading this atmospheric technosignature search is Sarah Seeger's team, who developed a Spectrophalanx Plot. This innovative tool allows astronomers to visually compare all spectral peaks in a gas molecule's spectrum and group similar molecules together. The team maintains a comprehensive natural products database of compounds generated by biochemical processes, serving as a crucial reference point when analyzing potential technosignatures. Taking this theoretical approach into practical application, the James Webb Space Telescope represents our first real opportunity to detect these signatures. The JWST's unprecedented sensitivity allows it to capture the faint light filtering through distant atmospheres when exoplanets transit their stars. Its instruments can break this light into component wavelengths with remarkable precision, revealing chemical compositions trillions of miles away. This detection method works regardless of whether a civilization is actively communicating. Unlike radio signals requiring deliberate transmission, atmospheric pollutants emerge as unintentional byproducts of technological development. A civilization only needs to be building and manufacturing, activities fundamental to any technological society. If we detected these compounds in the atmosphere of a habitable zone planet, it would prove the existence of technological civilization. There would be no alternative natural explanation, no astronomical process that could mimic the signature of nitrogen trifluoride or sulfur hexafluoride. It would provide definitive evidence we've been searching for. This approach represents a fundamental shift in finding other civilizations. Instead of waiting for them to call us, we're looking for their industrial footprint. This method acknowledges that civilizations might not want to announce themselves, but can't help leaving traces as they develop. Even civilizations attempting to hide might find it impossible to eliminate these atmospheric markers during development. A society would need to skip the industrial phase entirely or develop in an entirely different direction to avoid creating these telltale compounds. Astronomers have identified promising targets for this search, including planets in the TRAPPIST-1 system. This system, with 7 Earth-sized planets orbiting a cool red dwarf star about 40 light-years away, presents an ideal laboratory for searching for atmospheric technosignatures. Their frequent transits make them perfect candidates for spectroscopic analysis. This detection method works across vast cosmic distances. Unlike detecting night lights or heat signatures requiring close observation, atmospheric compositions can be read from many light years away with current technology, dramatically expanding our search radius. This approach transforms the traditional SETI paradigm. Rather than assuming advanced civilizations want to be found, it acknowledges most technological societies might be indifferent to detection or trying to remain inconspicuous. By looking for unavoidable side effects of technological development, we can potentially identify civilizations regardless of their communication preferences. The search for atmospheric technosignatures represents a maturing approach to SETI, one that moves beyond waiting for deliberate signals and instead looks for the inevitable consequences of technological development that no civilization can fully conceal.